My name is Antti Sunnari. This is my first Augmented World Expo talk, and I'll be introducing our company Dispelix, which is a deep tech company, and we do see-through displays for smart glasses, mixed reality, or let's say everything near the eye displays. The company was founded late 2015. And we are based in Finland and now opening a site here in the US also. So what we actually do and what we have actually accomplished is the world's thinnest waveguide, and it has still the same performance or better one compared to anyone else, and it works very well on augmented reality and mixed reality applications. To go through a little bit about what is the needs for augmented reality or augmented reality, mixed reality, whatever you called headset. And this is what we get from our customers. So it should be eyeglasses form factor as my glasses or those here. It should have an unlimited battery life. Everyone likes to wear it or watch movies all day long. At least 120 degrees field of view, diagonal, easy to achieve, and a sensor fusion so that you can have all the fancy stuff like tracking of the environment and placing virtual objects in the real world, and so forth, so forth. And we all know that this is not actually happening very soon. So for that reason, we see two different approaches to get there. One of the best examples to start with the small is Nord with their focal glasses. So that is very good looking device. It's consumer acceptance is good. You can wear it all day long, and it looks good. But it's missing a lot of those fancy things like tracking and field of view and those things. On other hand, there is another approach like with Microsoft. So build up everything there, all the sensors, sensor fusions, all the tracking, large field of view things. But you compromise or you actually pay it with the form factor to have that computer built on your head, actually. So how I see that we are going there in the very good form factor, and there is two different approaches. One is to start with the good form factor, and one is to start with all the sensors and everything. So, and Dispelix, we are doing waveguides, and why we do waveguides and what's the reason? It's hard work. It's much easier to do BirdPath or something like Nreal or someone else. So the main thing is the iBox and how to accommodate all the people in the world with just one optical solution without any mechanical adjustment or anything. So when we check the mechanical stability constraints for waveguides, we have gone as low as 300 microns. That starts to be quite fragile. It needs another layers to support. And on the other end, we have the form factor, how good it looks on your head. And then we check the human population. We have a minimum IPD coverage, let's say 70% of human population. And then we have full IPD coverage. And when we check these different kind of optical architectures, free space curved, light guides, waveguides without expansion, and then waveguide with exit pupil expansion. So we see that in our case, it's a standard line. So no matter what we do with the iBox or the iBox size, the thickness remains the same. So that's the key part of using waveguide with the exit pupil expansion. Couple of principles for the waveguides. So this is something we started to do 2011. So it's a one-dimensional expansion. So what we can see here that this is the in-coupling and the outcoupling area, and light travels from the in-coupling, so from the projector. It bounces through by total internal reflection to outcoupling, where it bounces multiple times and outcouples the user's field of view. This is very simple to design, as to say in the waveguide, and you can have a large field of view, everything, it scales nicely. But the hurdle, the problem, is the projector. How you make such a large pupil in your projector. So to overcome that, we need to expand the field of view in 2 dimensions, or not the field of view, but the exit pupil. So here we have a very small outcoupling. So the light couples inside the glass and start travel by total internal reflection. Then it hits on this EPE grating, and that grating beams everything downwards, so going up to down. And on the same time, each ray is split, and one part continues, one part goes down. And that is how we get horizontal exit pupil expansion in this case. Then, when the light travels to outcoupler, it gets a vertical expansion on the eye box. So in each interaction with the gratings, nanostructures we use, part of the light is outcoupled to user eye, and part of the light still travels further. So that is the key step, how we can decrease the projector size. And these architectures, on the other hand, they have some limitations on field of view. So, and I'm speaking only behalf of single layers, so one way is to stack these waveguides together, but our approach is a single layer. So what we are presenting in our booth is the DPX30. So there is a traditional way of doing 2D expansion. 1D grating incouples the light, and then it travels down and beams here and outcouples. The limit around 30 degrees for the field of view, diagonal, with the 16:9 aspect ratio. With different aspect ratio, 1:1, it's roughly around 40 degrees field of view. Another way is that you actually split the field of view going in 2 different paths, which is the bow tie here. And in that sense, we have a 2D grating. So those gratings beams the light in 2 directions. And then we split the field of view in the in-coupling, and then combine it in the out-coupling. This is, I think, what the HoloLens 2nd generation is using, this kind of architecture. I haven't seen it on but some teardown images. To pushing it even bigger field of view and pushing the limits where we can go with the single layer is to use only 2D gratings. We find the nice name mushroom forest because it's like a pillars on top. And in that case, the field of view travels inside the light guide in multiple directions and multiple different paths. And there we get the limit roughly 60 to 70 degrees field of view. And why to go through these different architectures when the field of view is increasing? The reason is that we need some room for the nose. So otherwise the footprint becomes bigger and bigger of the waveguide, and there is not any more room for nose in human. So pushing the bow tie in larger field of use and large eye box and everything, you actually get it too big and you don't have a room for nose. So this also, the mushroom forest, it also combines that in each interaction the light is spreading, so getting the exit pupil expansion and at the same time outcoupling. So our technology, as to say, and our waveguides, they are surface relief gratings. We are not doing volume holographics like some of our competitors and other companies in this field. Our key point is that it's single layer, and I come to why we think it's very important. And the full color, that's for the consumers. And the main technology for manufacturing is nanoreplication. And what we achieve with single layer, we achieve a cost advantage because we don't actually need less glass, and the yields and everything are better. And we try to be profitable company in this area where most of the companies are losing money. It delivers good form factor on a thickness, weight, and those points. Image quality, we don't have cross coupling between the layers stacked together. And it's even easier to get into volume manufacturing than doing multiple layers and stacking those together. So cost and wafer utilization. So if we think about, if we assume that each process step when you manufacture a waveguide, you have a yield of 98%. Then you end up in a yield for single layer, the total yield, about 87%. Okay, if you have two layers, the both layers have 87% yield, so then your total yield is 76, so dramatically lower number. And let's say in 3 layers, it's even less. And this is pure math, not anything else. And also, we get more wafers from one, more combiners, more waveguides from one wafer. Form factor and the thickness. So I just calculated our waveguide is 800 microns in a thickness. Then we have a protective glass, Gorilla Glass 400 microns, and then we have a 100 micron air gap between to optical insulate the layers. So we end up having 1.3 millimeter in thickness, and if you have 2 or 3 layers, the thickness just keeps add up. Then this is for the manufacturing and cost. So let's take one manufacturing line that can do 1 million waveguides, okay, and once again 100% yield. In our case, when we are single layer, we can get the 1 million from that line. If you have 2 layers, you get the half with the same running cost, and with 3 layers, well, that's 1/3 you actually achieve from that manufacturing line. So let's say in case doing 2 layers, you need 1 more line, manufacturing line, to achieve the same capacity annual. And the image quality, so we are going through builds and ramping up end of this year for full-scale manufacturing. So first of all, we don't have a ghosting or any ghost images like cross-coupling between layers, but also we can achieve very good MTF, which means the sharpness of the image. And these are from our builds. So the first build, couple of hundred, this is the MTF and what we get. And on a second build, we got even higher by changing a little bit of our design and make it compatible for volume manufacturing. And this is the highest one we have seen, and I think have anyone seen that high MTF on a waveguide. That's displayed on our booth 712. How we can achieve these like high MTFs, manufacturing and yields and everything? The key things are 3 points, and the first one is the waveguide design. So if you do waveguides, there is no commercial software to design and optimize these. So you have to build your own software. And that is what we have done. So we have our own custom software written from the scrap. And it's polarized. There is, we can adapt the spectrum of the LEDs or peak wavelength of the laser, polarization, phase. We can track polarization, cross-coupling, and everything. And it's not easy computing. So without our algorithms, just go brute force calculation for one of these waveguides. With a laptop, it would take 800 million years. So it's heavy computing. With our algorithms, how we optimize the structures, and using just 10,000 CPUs, we can optimize the structures in 1 week. So you need that kind of software to design waveguides. If you miss that, you cannot do a good image quality. Just the image on what we get from the software. This is different iBox locations and the field of view, what kind of shift there is, and then what is the actual products, what we made the prototype. So our simulation model agrees extremely well on the prototypes we make. Second, most important is to keep the pace. So we have in-house team to manufacture these waveguides. So once the design is ready, it takes us 4 weeks to have the first prototype. So we can iterate very fast and develop. So what we do, we use E-beam for fast prototypes, and we do the softwares and we operate the E-beams by ourselves. We have all the nano imprinting, etching, all the other phases in-house, or we collaborate with the university labs and research institute labs. And we can do masters for volume manufacturing by ourselves. We also have characterization, so we can measure everything from this, what the spectrum is coming out, what is going in, what is MTF, what is color balance, and all of these things. In a mass production, we have our own team, which is bringing, or teams which bring the design after its proof of concept, it's accepted to go into volume manufacturing. The team of 10 people takes it to the full manufacturing. So they go through to the foundry, show them what to do, what are the parameters, then collaborate with the foundry to get the yield up and the manufacturing process running. And we have very short loop from mass production prototyping to the design table. If they come back that, okay, this part here in the waveguide, these nanostructures, we cannot actually replicate very well, or they affect a lot of yield. So we can go in the design table and change it. We have a now supply chain for our waveguides, and we have done 2 builds already. And end of this year, we are in high volume manufacturing. So the product we are ramping up to say it's the world thinnest, so just 1.3 millimeters total with all the covers and everything. We haven't seen better MTF or image quality sharpness, and it's easily to take in the volume manufacturing. Some other parameters, the field of view is 30 degrees, 16:9 aspect ratio. I think it's very good on the smart glasses. And by the way, this product is it's not aimed for any mixed reality, HoloLens or Magic Leap type of devices. It's more or less on motorcycle helmets, smart glasses, all the other that kind of use cases. And well, you can see the data here. So what we think about diffractive waveguides, and hopefully I address these, so these are ready for real volume products. So waveguides, they enable very good form factor for any devices, smart glasses or other things. It's very thin. Image quality, the sharpness, color balance and everything, it's for professional and consumer use level, so that's there. We have done manufacturing builds and the yields are very high, surprisingly high in those. And it's ready end of year. What we are missing in this game or this thing is very small, very high performance projector. Our current projector is about 8 cc, cubic centimeters in volume. I would love to see 2 cubic centimeters or something projectors. These are the dev kits we already shipped out. So what there is cables, and then there is a driver board and projector and a frame for the waveguide. Okay, thank you. Come and see our demo.